Hello! Today I'm going to tell you about possible workflows to analyze your simulations using Python. So you perform your Cactus simulation, you study binary black hole mergers, binary submerges, neutron stars, whatever. Now you want to know what's inside. You want to make a visualization, you want to extract gravitational waves, all sorts of post-processing and analysis. So today I'm going to explore different ways where you can do so using Kuibit. Kuibit is the official post-processing package for Einstein Toolkit. So for today, my plan is first, I'm going to give you a very general introduction to Kuibit. Second, I'm going to tell you a little bit about installing and setting up Kuibit on your cluster, on your computer. I'm going to explore some examples to give you a feeling of how you would use Kuibit. And finally, I'm going to explore possible workflows on how you could use Kuibit for your purposes. So first, let's start with what is Kuibit. So Kuibit is the official library for post-processing and analyzing Einstein-Toolkit simulations. So when I say post-processing, I mean two different aspects. On one side is making a visualization like this, where we can get a sense of what's inside. But this is not necessarily like a quantitative. I mean, it is quantitative, but we don't learn anything too detailed about the simulation. We don't learn how much gravitational waves are emitted. We don't learn how much energy is in the system. We have to crunch the numbers to get those answers. And so there's a second part in post-processing. Post-processing is taking the data that we already have and producing new analysis, new ideas that are derived from the data that we already have. For instance, we can compute gravitational waves. So our simulations typically compute psi4, the Newman pairs psi4, which is not precisely the strain that would be observed by LIGO, Virgo, LISA, all the gravitational wave detectors. So there's additional steps to get to the strain. And this is part of the so-called post-processing. Another example might be we output pressure and density, and we want to compute a derived quantity that depends on these two. So there is this aspect of making nice and useful plots, but also making quantitative predictions or quantitative analysis. So Kuibit does both. Helps you making visualization, helps you producing useful post-processing and quantitative analysis. And in this, the fundamental idea of Kuibit is that Kuibit will take care of the low-level details for you so that you can focus on what matters the most, that is your science. You run your simulation, and you don't have to think about the details about how the data was output and what folder it lives and all stuff like this. So, and the keyword that we have for the slide here is library. So Kuibit is a library. It's a Python library. So it can be used write your own visualization and post-processing scripts. So you can import it and use it. But as we'll see, there's also very useful examples that you can immediately run for your make visualization like the one that I have here on the left, or to make something like this. Okay, so this is what Kuibit is. What I want to stress is that, so for today, I don't want to give you a full overview of Kuibit. I don't want to build your understanding of Kuibit from the ground up, because there's already a lot of material for that. So these three videos, which we recorded over the past few years, particularly the last one, is a very detailed tutorial that guides you from knowing nothing to being able to do some useful stuff with Kuibit. So for today, I'm going to very briefly touch upon these ideas, but I want to focus on a different aspect, so that this new video is going to be part of a larger collection of videos that you can use to learn about Kuibit. So I highly encourage you to check Kuibit out and for more information. Specifically, this last tutorial I gave last year, or 9 months ago, apparently. So what I also want to emphasize that Kuibit has very good documentation. It has what I consider 4 different types of documentation. On one side, there's pages, which I call usage pages, which describe sections of the package or specific modules in the package to help you understand how they're designed and how to use them. And there's tutorials where you can learn about how to use those various modules. Then there's a comprehensive description of all the APIs, application program interfaces, so all the functions with signatures, with description, and stuff like that. And finally, there's a always growing collection of examples that are useful and to teach you how to use Kuibit, but also immediately get started with some applications. And I'm going to show you this in just a second. But let's explore the website. So this is the link. You can just Google Kuibit and you're going to find it. And this is what the website looks like. So for instance, if we want to look at the usage pages, we can look at how to work with horizons. There's some information. There should be a K. It's not VT, it's BTK. There is information about grid functions with some useful information about design and some pitfalls. So this is the usage page. Then we have the tutorials. For instance, we can go again with grid functions, where we can learn how to do stuff with Kuibit. We have all the APIs, which we can find, for instance, if we go on sensitivity curves, here it's all the different APIs. So these are all the sensitivity curves that we have from Lisa and so on. And finally, we have all the tutorials, all the examples. So I don't know, we can look about coordinate velocity. So it gives me a short description of what this code does, and then it gives me the code so that I can learn from here. The examples are developed by me, most of them. So most of them are developed in a very Kuibit way, quote unquote. That is what I think being probably the best way for the current features that are available in Kuibit. And in general, if you want to know about all the features that are in Kuibit, there is a features page that has a long descriptions of what's inside. So this is overall description of what Kuibit is and where to find documentation. I think the documentation is very, very useful, very, very important, and it can help you a lot. So do check the documentation. But of course, the documentation is not the end of the story, and documentation most likely is going to assume a pre-existing knowledge about certain topics. So it's very useful not just to learn, look at the documentation, but to get in touch with other users and developers of Kuibit. So particularly me, which I'm the lead developer of Kuibit, you can get in touch and with me in these 3 ways. You can send me an email with this address. You can join the Telegram group for Kuibit, where you find developers and users, and you can ask questions, and someone will probably answer the question. And or you can provide feedback, or you provide comments, or you can learn about the most recent announcements about Kuibit. And finally, if you catch me anywhere in a conference at University of Arizona, or at least right now, as the time of speaking, I'm very, very happy to help you get the most out of Kuibit and to point to where you can find more information or how we can improve the documentation so that it's more useful for everyone. So that's it. That's it for a very, very brief introduction of Kuibit. I want to I want to make 4 points quickly before I discuss more. So Kuibit is completely open source, and there's a paper in the Journal of Open Source Software. So if you use Kuibit, it would be great if you also cited this paper. As mentioned, you can join. Probably the best way to learn about the development of Kuibit is by joining this group or by sending me an email. And this is what a Kuibit is. This stick here. So Kuibit is a Tohono word, and Tohono is the local indigenous population that we here in Tucson, and is the stick that is used to collect the fruit from saguaro cacti, which are these big cacti. So my personal slogan for Kuibit is harvest the fruit of your cactus simulation with Kuibit. And before I move to the next step, I want to acknowledge what made Kuibit possible. First of all, I want to acknowledge that the Kuibit was built in many ways following the example and the design of a pre-existing code called Cactus, developed by Wolfgang Cashtown. And it was built using the Python ecosystem that made it possible, particularly NumPy, SciPy, H5Py. These are very critical packages in Kuibit. And there's funding agencies, in particular Texas Advanced Center for Computing, National Science Foundation, and NASA that supported me for the past few years, and where I partially use my time to develop Kuibit. Okay, so this is a very, very short introduction about Kuibit, and I probably didn't tell you much about Kuibit. Again, what I want to stress is where to find more information, the website, and how to get even more information if what's on the website is not available. So with that, let's now start looking at Kuibit in a more hands-on way, at least the first few steps. So here I collect some pages to describe what could be the first steps, or it could be a progression to learn Kuibit. So for instance, there's this first step, which I think is a first step here, where I describe some ideas on how to to learn Kuibit. For instance, using the examples, trying to reproduce the examples so that you can learn more. And here I walk through some of the keywords, and so this could be a good place where to start learning Kuibit. There's more recommendations for examples. See where I have a recommendation, which is essentially setting up some variables. I'm going to describe this in a second, so that you can more effectively use these codes. Finally, I want to mention that Instant Toolkit comes with Kuibit. Kuibit is an official package in the Instant Toolkit, and with this, it comes also with all the examples that we have are included within the Instant Toolkit. So if you have the Instant Toolkit somewhere, then you already have lots of useful codes from Kuibit, and I'm going to discuss that in a second. So let's first look at how to install Kuibit. And now on most systems, I would say, well, just run pip with the user flag, with the upgrade flag, or if you want to have a specific version, you can specify the specific version, and this will install Kuibit. You don't have to do anything, it's just there. And we can maybe have a look at an example where this works. So pip install user upgrade Kuibit. Maybe I'm going to make the font larger. So now I'm on a supercomputer, and now I'm installing Kuibit version 1.4.0. I had a previous version, and now it got updated. I think by the time you're going to watch this video, this is most likely going to be the most recent version of Kuibit, and is going to be the version of Kuibit that is officially bundled or associated with the latest release of the Instant Toolkit, which at the time of speaking, is going to be something like released in May 2023. So we probably call it Instant Toolkit 2023-05. But you can check the official webpage to see what version to use. So as you can see, pip perfectly worked. There were no issues whatsoever. But this is not necessarily the case, especially if you go on other systems, because Python is a little bit messy. As we can see from this comic from XKCD, there's a lot of possible ways to handle Python. So now I'm going to go on my computer, or at least the computer where I'm recording this video, to show you an example of what happens if we install Kuibit with the same command on my local Debian computer, and I get an error. I say, okay, Debian wants me to use virtual environments. So in that case, I would say try to find what is the most appropriate way to install in general Python packages. Kuibit behaves exactly like a Python package. So as long as you learn how to install Python packages on your system, then you're good. But in general, I'd say this is a pretty good way to install Kuibit. And of course, if you know more, please apply what you know. Okay, so now that we have Kuibit, the package, well, let's check that indeed we have Kuibit. So for that, I can open a Python session, and I can just import Kuibit. Import Kuibit, well, it works. And I think there's probably also a version. Yes, so we checked. Indeed, we have the latest version. And as we can see here, this is what I meant with we have a library. This is how Kuibit works. It's a Python package in the same way NumPy is a Python package, SciPy is a Python package, and so on. Second, I would recommend, so now here I have my Cactus folder. And there's we have our utils, analysis, and there is Kuibit. And Kuibit, there's an example folder. And I realized that there's a bins missing from here because the bins is what we really want. So here is all the examples that we already found here, already bundled with the Einstein toolkit. So if you have the Einstein toolkit, you have all these examples. So you can open them up and see what they look like, or you can immediately execute them. Now, you could execute them with / plot whatever, or you can export. Open a Pinot thread, you can export a path, and then provide this directory, which is what, I mean, I'm not going to do it. I don't know what happened. But you can add this directory in the same way I'm doing here to your path, so that what happens is that when you do so, all the scripts become executable from everywhere. Like we can check. This is this is where the script lives, which is example bins, exactly this. So yeah, there's a missing bins. So now what I would like to do is, and I highly recommend doing this because it gives you a very quick way to get some plots done with simulations. So for instance, now I have a full simulation in this folder. What I want to do is I want to show you possible workflows to work with a simulation like this, or any simulation. So now that we have the example, what we can do is we for instance, we can plot the we can make a plot of Psi4. So now Psi4, we don't need most of this information, but we can also move this. So I'm going to plot Psi4 and M are the two multipolar modes with 2, ML equals 2 and M equals 2, and I want the first detector. So when we measure gravitational waves, the multiple gravitational extraction radii, and we want the first one. I already had the output here, but we're going to produce it again. Now this is a binary black hole simulation, and what I want to point out here is that, so this is a full simulation, and it's taking a little bit of time. It took 17 seconds just to prepare what I call the sim there. So essentially, when Kuibit, when we're calling Kuibit, when we're using Kuibit, one of the most critical steps is to understand what's in the simulation, and is to make an index of the variables that are available and where to find them. Now, what happened here is that Kuibit went through all the folders and again prepared an index, understanding what's inside. And when we use scripts, this typically has to be done every single time because we cannot assume that the underlying data hasn't changed. So sometimes using scripts, we get that indeed there's a little bit of a waste of time, especially when we want to run multiple simulations, when we want to run multiple analysis on the same simulation. So maybe also we can have a look at this plot Psi4 to just get a sense of what it looks like. So I think I can do this. Let's see if it works. Oh yeah, of course. Well, then Cactus, it didn't work. Repos, Kuibit, samples, bins. Okay, so I'm kidding. What I want to do is this. Oh. Yeah, to see what it looks like. So we have some warranty information. Warranty. There's no warranty. Some copyright information. We have our imports, and then we have a lot of boilerplate on what we want to do with command line arguments. And then what we're doing is we're preparing SimDir here in this step here. Then we're reading the gravitational waves that are available. We're doing some error checking. We're plotting our Psi4, and then that's pretty much it. We are saving our figure. This is what the script looks like. Most of this, again, is boilerplate to be more general. Okay, now we ran our script, and let's have a look at the output. So we have our Psi4. Here is running hard because it has to record a 4K video. Okay, so this is what it looks like. like an honest stat for a plot. But what I was mentioning before that I want to stress as I'm building towards the idea of workflows is that if we have this data here, we can make an index once and just use it all the time. So one mechanism to do so is using pickles. So pickles are an idea from Python to save an object locally on disk and reuse the same object multiple times. So what we are doing here is with this picklify script, which is another example, we are scanning all our folders, understanding what's inside, and preparing like a large index, comprehensive index with all the information so that we can use this sim.pickle to skip all the preparing sim.dir step all the time. Now, here we have to be careful because once we prepare the pickle, we're skipping the step of understanding about the context of our directory. So we have to do this all the time that something changes. For instance, if we add a new checkpoint here, so output 20, we'll have to produce another pickle. Otherwise, we're going to use data that doesn't reflect the content of our simulation. So now this takes a little bit longer because it's a very comprehensive and thorough index of our simulation. So we can let this here for a second. I mean, we don't particularly need this, but let's we can let it run. Now, what I want to discuss next is I want to start getting into the idea of like scripts and workflows, and why all the examples are scripts, and why they're not like notebooks, and what possible what possible workflows one might adopt to use Kuibit. So, well, I mean, we can let this run. Okay, still the same there. Okay, so this took 2 minutes, but now when we have our previous, yeah, we can do pickle file, sim.pickle, and now this should take much less time because of the index. So let's have a look. Yeah, so the prepare sim.dir took 1 millisecond, so it was much faster. Okay, so so now let me go back to my slides. I want to talk about I don't know why they're not centered, but you know, let me maybe move myself. Yeah, we're not going to need this much. So I want to talk about why I like scripts. Why all the examples are scripts, and what I think are the main advantages of using scripts. So first of all, writing scripts, I find it very portable, very robust. Scripts are self-contained, and easy to share. Essentially, when I have my scripts, I can easily make them examples, and I can easily share them, and they're immediately going to work for all the simulations. There's nothing that has to be changed. No path, nothing, no code. So there's a lot that can be done just by running these scripts. And so I find them very, again, portable, robust, and self-contained because you can just do one thing, and everything that has to be done for that one thing is there. They're also good to learn how to achieve specific goals because they don't hide anything. Everything has to be there or inside Kuibit. Second, maybe also very important, is that when I write a script, I can take advantage of all the Python tooling for code development. So I can use linters to make my code look pretty. I can catch error very easily while I'm writing the script using static analyzers and stuff like that. I can write tests, and all of this is very natural when it comes to writing scripts. And in this, I think the writing scripts promote code reuse and good software engineering practices, in the sense that when I write scripts, I write functions, I make them small, and I can easily transfer these functions in a library if the functions become too large. So scripts by design have to be small. Everything that is too large typically end up as being part of the library because it's an important feature, and most likely it's an important complex feature. And in this, there's a lot of code reuse. Because again, the useful parts are generalized and put in a library, and everything else is just an application, essentially, of a function in a library for a specific purpose. With scripts, I can easily put them on Git, or GitHub, and I can easily run version control and continuous testing, and which is great to ensure that I can easily check, go back to previous version and check when things changed. Then with scripts, for the most part, they don't have stale states, and what I mean is that if we ignore the pickle for a second, we can guarantee that the script will always produce the same output when run with the data that I have. This is not the case for interactive sessions because there is a history, there's a state. So this is, to me, is very important because it's a guarantee that I haven't messed things up. It's a guarantee that I can reproduce the result. It's not that I mixed the order of cells and stuff like that and I get the different output. And finally, I find scripts very useful for composition and automation. So for instance, I can call a set of scripts at the end of my at the end of each checkpoint automatically. Like I can have the checkpoint, the simulation ends 30 minutes before the end of the wall time, and then I automatically, as part of my run, the new plots are made, so I can immediately see what's happening. And I can also compose different scripts. Like not all the scripts produce plots. I can some scripts produce text, and I can use all the Linux, Unix utilities to compose multiple scripts and to do complex stuff that is well beyond the realm of Python. So this is why I develop all my tools and all my scripts and as scripts. And this is why I typically encourage like a script-based workflow as opposed to like an interactive Jupyter-based workflow. So now I want to use the rest of my time to think about how this can be done. So I want to present some possible ideas on different workflows for writing scripts and using scripts for your analysis. For that, I think I have one. Yeah. So here I divide the list of workflows in two areas. On one side, we are going to bring our codes to the data. So typically, we run simulations on a supercomputer, and we are going to bring our scripts to the data. And so we have remote execution. So we not analyze stuff on a supercomputer. The other alternative is that we bring the data to our machine and we run our stuff on our machine. So I want to touch upon some of these ideas, and the list is completely not complete in the sense that these are some of the ideas I've thought, and I'm going to tell you what is my preferred methods. But I want to discuss possible ways to again to do what we're trying to do here. So using scripts and to understand the content of our simulation. So let's start with the first script that is our data is on the cluster, and we analyze the data by running stuff on the cluster. So now the question is, how do we look at the result? So let's have a look. So we can go back to our plot. And so one possible way is to use sorry about that. Yeah, I have to move. No, I want to move my head here. Okay. One possible way is to use so pass through the graphics through the SSH session. So I can use for instance, display or I don't know, any type of like command that produces graphic output and see what it looks like. But as you can see, this is quite slow because we have to render the image or render the application, transfer the application like the pixels to my computer, and then we get our plot. This is what it looks like. And so, I mean, this works, probably not the best. Similarly, sorry about that. What we can do is we can SCP. So I'm going to get test. I'm going to get my psi for 0. We can SCP, and when we SCP so we are copying the image on our computer, and then we can just look at the image on our computer. Now, again, I don't think this is the best way to go about doing this, because it requires every time we produce something to copy it over, which can be very time consuming and is not a very tight feedback loop. So when I see that there's something wrong, I have to regenerate the image, I have to copy it over. And so I don't think this is very effective. But it's a good and simple way because it doesn't require any tool, it doesn't require any understanding of anything. So these are first one. Second, there's a tool called SSHFS. FS stands for file system. And what we can do is we can mount our remote file system locally. So we can do SSHFS. We can mount our simulations folder. Okay, so this was the correct instruction. And now if I look at my mount point in my TMP, TMP mount, and I can go in simulations, and I can, there's a link. Okay, I know what's going on. But yeah, so what I could do here is I could find, if now I have a sim link to a different disk that is not mounted, so let's not get into detail, but here I have I can see my files remotely. So I can open my remote files as if they were local. And I think there's ways to do this as part of the graphical interfaces in like Linux distribution, like Ubuntu and Debian. I think they have ways to embed this in their graphical interface so that essentially you see remote files as if they were local. So you can just open them very, very easily. The catch with this is that, especially if your connection is spotty, it's not super reliable, there can be high latency. It can lead to sometimes you will just get errors because you cannot reliably have a connection going. So, or maybe you're on like public Wi-Fi's and so on. So this works, is nice, but depending on your internet configuration, can be not necessarily the best way to look at files. So my next step, or what's this? My next step here is to so my personal solution to all of this is to use Emacs. So right now we're looking at Emacs, and we Emacs has a feature called TRAMP, called Transparent Remote Access Multi-Protocol, which allows me to open remote files as if they were local. So all that for instance, when we're here, what I was doing here is my Control X, Control F is my way to open files, and I can open my file. Then when I do this transparently, as Tramp says, I'm downloading the file and I'm displaying the file as if it was local. So everything happens again transparently. But of course, this solution requires Emacs. I think there's something similar for VS Code, but I've never used it, so I don't know. Finally, a possible workflow is to use remote desktop solutions, such as VNC and RDP, which are protocols to see the desktop, or the quite literal desktop of as if it was like of the remote machine, as if it was like a local machine. Typically with not particularly high resolution, not particularly high refresh rate, but it's good enough to be able to do what we want to do here. So, but the catch with this is that typically the cluster supercomputer has to support this. I find that many supercomputers do have some infrastructure to do this because it's critical to do visualization. So if you want to visualize large amount of data, there's some there is a visualization node or visualization way to again to have some form of like remote desktop. So these are possible solutions to do all the analysis remotely and then look at the results quickly. So look at the results as produced by plots that are saved as PDF, PNG, or whatever you want. Or well, actually in the other two cases, which you can do, like in VNC, or you can do you can plot with plt.plot in Matplotlib, and you'll just get the result as if it were produced like quote unquote normally. The other possible workflows is to look at is to bring files on your local machine. Now, for most large simulations, of course, you cannot bring the entire simulation. The entire simulation can be terabytes, and multiple simulations can be multiple terabytes. So most often, you don't have the luxury that you can bring your data on your computer, especially if you don't have like a large hard drive. I have an external hard drive, so I can fit a lot of stuff. But again, typically you cannot bring the entire simulation. So what you can do instead, you can use rsync to bring a selected selection of the files that you're interested in. So suppose, for instance, you want to work on gravitational waves, then you only need the multipolar moments. You don't need anything else. So what we can do inside here is, let me make these big deals again. Let's see. Okay, here, what I have is a rsync line. What we're doing is we're all including, now 2, we don't necessarily want to, oh, sorry for the mess. What we want is a multipolar, which stands for MP. And so what I'm doing here is rsync. There's also a compression flag in here. I think the Z is verbose, Z is to compress. E, I don't remember what it stands for. And we're including the MP files. The rsync has this not particularly nice syntax to just include one type of files from our remote host here, which is this PFE and the simulations that we were looking at before. When I do so, what happens is that rsync tries to looks at the files and looks if there's new files. Now, that's not what I want, but copies over all the files that match. In this case, this so probably we did like a, probably this is what we want. Let's see if this works. Yeah, so here we're copying all the multipolar files. Now, if we look in our simulation, we're going to see that we have same structure, but with the multipolar files. So, so now we can use our Kuibit scripts, and as long as we have the files, so for instance, to make just go here. Well, this is probably too small, but size 4. I don't know if we can do this. Yeah, we can make a file. This is going to be the first 35M, so not much. But we can probably do some. I mean, we can make plots like this by copying the files that we're interested in over. And again, many of the files are not particularly big. Like, you know, it depends. But like, if we only select specific types of files, these are they don't have to be terabytes, can be much smaller. So we can do all our analysis locally, which is very quick and effective way to run analysis. Again, the catch here is that we have to copy the files over, and we have to know what files we want, and we have to copy the files that are, we have to have enough space for all the files. So this is one possible way. The other way is to, again, use SSHFS, but in this slide, instead of using it for looking at visualization, we use it to run the code. So in this case, we ran the code and we look at the visualization from our computer. In this case, we run the code on our computer, move the data remotely. Now, this can be particularly ineffective if you're working with large amounts of data that have to be transferred over to your machine, because when you do SSHFS, you still have to transfer data over. So this is maybe fine for like multiple data, like time series and stuff like that. Probably grid data wouldn't work as well. For that, you can reduce the size of the data if you know what you're interested in, and reduces the size of the data, especially if you want like specific iterations only. With Kuibit, you can save like the chunk of data that you're interested in and just copy that chunk over. So let's see if I can find. I think there's a function called save. So this works for a series as well as for grid data. So we can save. So there's a function called save that allows us to save a portion of the grid data that we're interested in for a specific iteration of all the iterations that we want to disk in a highly compressed and way, so that if we probably also downsample, or if we are not interested in having like super high resolution. So this is especially good for a 3D visualization, because typically what we want to do is we want to have something that we can look at. So we want to have, we want to take the data and do our explorations on this data. So we can save our data. And I think there's an example that does this, but I don't remember the name. Save resampled grid data. So this example takes a part of the grid, the specific iteration, and produces an MPZ that contains the data, and we can just load this MPZ to do all the visualization that we want to do. So this is, I think, is especially good method for 3D visualization, because again, it's very convenient to be able to have like a graphical session on our computer. So again, this is the possible workflows that you can adopt if you want to. This is what I thought, but I'm sure there's way more that I'm not aware of. What I personally do is I typically use this to have a quick inspection of the data. Then I often copy the data over on my my computer when I want to do larger analysis or like production analysis, unless they are like a large visualization, large movies, then I will do that on a computer. But if I have on a supercomputer, but if I have to do so, typically I still save on my desktop computer like a couple of slices, a few iterations, so that I can produce and tune the script as I want, and then I run everything on the supercomputer. Then, especially for 3D visualization, I follow this third method, which I downsample the data, just look at the region of the grid that I'm interested in, I fix all the stuff that I want to fix, and then I run in batch on the supercomputer. So this is a few possible script-based workflows that you can adopt if you want to follow a script-based approach. But in this, there's also like a second aspect, that is how we develop scripts. It's very, very, very useful to be able to do interactive stuff. So for this, I can think of at least two possible solutions, ways to use Jupyter notebooks. Again, mostly to get a sense. Then I would personally recommend putting the completed work in a script and use scripts. Using tunnels. So SSH tunnels look like, let's see if I have something. Yep, so here I have an example of a SSH tunnel. So what this L is, yep, so for interactive development, I see at least two ways. Again, once again, this list is not complete. This is what I thought about. I'm sure there's many, many more ways to do so. So one way is to use Jupyter notebooks. Again, mostly to get a sense. Then I would personally recommend putting the completed work in a script and use scripts. Using tunnels. So SSH tunnels look like, let's see if I have something. Yep, so here I have an example of a SSH tunnel. So what this L is what tunnels. So what I'm going to do is I take my remote server, like host name, take the port where Jupyter is running. So I'm running a server in my remote server, in remote cluster, running typically on port 888, 889. Then I map it to a local port, and then I can just connect my Jupyter instance to that port. So in this way, I can run something remotely through SSH, but have like a local interface. So this is one way to run interactively. Second, what I personally do is I have my scripts here. I start writing my scripts. Then I open with, again, in this case, I use Emacs. I open a associated REPL, associated interactive session. So what I can do is I can write my script here. I start writing my script here. So, and I can send the script or portion of the script to my REPL. So I can, in this case, I sent the entire script, and I can see what's happening here. So I can start, I can develop my code here and do everything interactively here. So I already building up my script while I get also the experience of interactive session essentially. So, and when it comes to plot, I can make plots where I can just save the plots directly into a file and look at the file. For instance, suppose import matplotlib pyplot as plt, import numpy np x equal np in space 5, 10, 100. Then I can do plot xx, and then I can have my So now if I change this, I can automatically get the new plots. So in this way, I get the, in my opinion, the best of all worlds. I can get some interactive session going on. I can do explorations, but in the meantime, I'm building up my scripts. So then I can finish the script. I can put all the boilerplate to make it available for general use and put it in my folder and run the same code for all my simulations. I don't have to change anything. And I can also distribute the script to other people, and other people can use it. So this is my personal workflow in this. So let's see if I have more to say. I want to stress that I think Kuibit is a great place to share codes. In the same way Einstein Toolkit and Cactus helped people share their thorns, I think Kuibit can be used to share visualizations and post-processing. And I think one of the best ways is precisely using scripts because they can be very portable. And Kuibit is very much openly developed, accessible. I think it's a very extensive comments, and I hope that it's easy to extend. I think it's a great place where one can learn a lot of details about software engineering, best practices, and stuff like that. So I encourage you to go and check out not only the website with the documentation, but you can check out the GitHub page where you can see all the development on the side of development, and you can have a look at like continuous integration and the details of how to run this and develop this. So finally, I'm going to once again bring this slide up to once again stress that this is work was made possible because of pre-existing work that was critical from post-Cactus to the Python ecosystem and also the funding of agencies. And I do really encourage you to join the Kuibit user group and interact with the development and to contribute to Kuibit. And always feel free to reach out to me. I'm really, really happy when I get emails of users that use Kuibit, and I want to help them get the most. So with that, I would say I will typically conclude my presentation saying that I'm happy to take any questions, but right now I don't know if I will be able to take any questions. So in case you have questions, do ask people around. Maybe we'll be able to answer, or send me an email, or reach out to me, or join this user group. So with that, thank you very much for your attention. And as a final comment, I mentioned some of the workflows that I thought were possible, but please reach out to me also to tell me about different workflows so that I can update this presentation. We can have a collection of possible ideas and ways to get stuff done. Thanks for your attention.